It's important to remember that there are different modes of navigation. For instance, you would not use celestial navigation in a harbor or close to land. Instead, you would use visual piloting techniques, such as matching landmarks on land to a chart in order to determine your position that way. Likewise, as you approach land from the open ocean, you can transition by noticing things like the change in water color, the smell of vegetation or human habitation, changes in clouds, bird activity, waves, etc. That'll all help guide your transition from open ocean or celestial navigation to piloting techniques near shore. Accuracy is a little bit less important in the open ocean. Of course, there are still rocks and shoals for you to trip over along the way, but for the most part, you're going to know where you start and where you're going to end in the route along the way. So if you're shooting celestial objects to an accuracy of about 3 miles, that's going to be an A+. Anywhere less than 10 miles of accuracy is perfectly okay. It's a big mind shift difference from terrestrial navigation, but again, in the open ocean, you're going to have a rough idea of what dangers are out there and how far you need to avoid them by. So celestial navigation is used when you're far offshore. None of this land as a hazard to navigation business. Instead of using terrestrial landmarks, you're going to use the lighthouses in the sky, the planets, the stars, the moon, and the sun. But in this film, I'd like to talk about using those lighthouses in the sky and establish some shared vocabulary so that we have a common knowledge base going forward. So for terrestrial navigation, there's usually a landmark, a lighthouse, an island, etc. And you're going to use a compass bearing to that to determine a line of position. Using your compass, using other tools, you can determine that you're somewhere on this line. If you were to have, say, a second island or a second object, you could take a line of position from that and you would get your fixed position at that point. That's the essence of terrestrial navigation. The problem is when we use celestial navigation, the lighthouses in the sky, they're just so far away that they result in a different line of position. So when we're dealing with the lighthouses in the sky, we have to take a bigger picture. We have to think about the whole Earth. Instead of just some island out there in the ocean, we've got the sun. It's got its geographic position, the spot on the Earth directly beneath the sun. And we're going to use our sextant to determine our distance from that spot. But the result is instead of a line of position, it's going to be a huge circle of equal altitude. But the principle applies. A circle of position, a line of position. If we have two celestial objects, each with their own circle of position, we can help determine where we are on the surface of the Earth. And then finally, if we have a third celestial object, we can pinpoint our position. And say, here I am. So understanding a little bit about this vocabulary is going to be really important going forward. So any celestial object is going to have a spot on Earth directly beneath it. So if you were standing there and you looked straight up, you would see the sun or the star or the planet. That position moves with time as the Earth rotates, right? So understanding where that position is very important. So let's say at a given moment, it's right here. This is what's known as the geographic position of the sun. It has a latitude and a longitude, but we're going to use different vocabulary for that in celestial navigation. The equivalent of this latitude is called declination. And for example, the sun, over the course of a year, changes its declination from the northern hemisphere to the southern and back with the seasons. Likewise, the moon, the planets, the stars are all going to have a declination. We also need another term to determine this position, this geographic position, and that is going to be equivalent to its longitude. Now, we set Greenwich, England, as the 0 point for longitude. So that's just a terrestrial notation. So Greenwich, England is the 0 point of longitude, and anything west of that to the sun's geographic position or a star's geographic position is known as GHA, Greenwich Hour Angle. So declination or latitude and Greenwich Hour Angle or longitude are the two ways to describe the geographic position of any celestial body on Earth. So after that theoretical discussion, let's go back to the boat. We'll use the whiteboard and run through a few examples. In the first part of this course, we took a quick look at the Nautical Almanac, focusing on the standard corrections for dip and altitude correction. The Nautical Almanac can also provide you with declination and Greenwich hour angle of any celestial body at any time. This position is called the Geographic position, can be found in the daily pages of the Nautical Almanac. It's important to note that all of these times are in Greenwich Mean Time, sometimes known as Universal Coordinated Time. You can find information for the sun on the right-hand page, the moon also on the right-hand page, the stars on the left-hand page, and the planets further out on the left-hand page as well. Aries is used in conjunction with the stars for determining the geographic position or the GHA or declination of any particular body. At any moment, there's a spot on Earth directly beneath any celestial object, so that if you dropped a line down from the celestial object, it would impact some spot on Earth. That spot, as we've talked about previously, is defined by its declination and Greenwich hour angle, or its latitude and longitude. It is important to note, though, that declination has some interesting properties when you think about the different bodies that we use. For instance, on Earth, there is the Tropic of Cancer and the Tropic of Capricorn. Those define the upper and lower limits of the sun's declination. So over the season, at the equinox, the sun's declination is at the equator. At the summer solstice in the northern hemisphere, it's at the Tropic of Cancer, and it continues down and kind of oscillates back and forth over the seasons. So this changing of declination for the sun is an interesting property of just how the Earth and the sun work together. Also, other bodies have different properties. So for instance, stars, the declination doesn't really change too much over the course of the year. So any given star that's out there typically has one declination and it remains there most of the year. Whereas the moon's declination does. Remember that we mentioned that the moon is very close to the Earth and it kind of follows its orbit around the Earth in such a way that its declination changes very quickly and more significantly than the sun. So we're going to learn how to determine declination very precisely later in the course, but for now I wanted to work through a quick example problem. So on 1 January at 0100 GMT, what is the declination of the sun? So for this, you would need to go into the daily pages of the Nautical Almanac. And so I've printed out this close-up version of the daily pages for the 1st of January. And you can see that over on the, it's on the right-hand page of the Nautical Almanac, but on the left-hand side, there is the sun column. So let's pay a little bit closer attention to this than we have in the past. And you'll note that everything is given in GMT, Greenwich Mean Time. So it's important for you to be able to understand what time you're looking for in Greenwich Mean Time. On the daily pages, there are typically 3 days. So the 1st, the 2nd, and the 3rd. The sun column lists its GHA, or Greenwich hour angle, and its declination. The Greenwich hour angle is usually pretty easy to pull off the table. You just simply note which hour you're using and pull the data off the table that way. And again, later we're going to learn to be more precise about this. Declination can be tricky. For whatever reason, the people who wrote the Nautical Almanac only write the whole degrees of declination periodically. Right? So it would be easy at, say, 0100 to get the declination wrong. The correct answer in this case is going to be south 23 degrees, 01.3 minutes. So it's not just 01.3 minutes, it's south 23 degrees, 01.3 minutes for 0100 GMT on the 1st of January. So we'll learn more about this in the coming parts of the course, but for now, understanding where GHA and declination are located for the sun is going to be important. Remembering that every celestial body out there has a spot on Earth directly beneath it, such that if you dropped a line down from it, or a weight, or another stone, it would impact the Earth in that spot. That spot's called the geographic position. It's defined by its declination, as we've learned before, and also its Greenwich hour angle. Diving in a little bit more deeply into this Greenwich hour angle business, we want to specifically state that the longitude of this spot is called the Greenwich hour angle. However, it's not the western or eastern longitude. Instead, it's going to be measured always westward from Greenwich all the way around the North Pole and back. So for example, if you were just a little bit west of Greenwich, your longitude and the GHA of the body would be the same. There's no west, there's no east, but the number would be the same. If you were just a little bit east of Greenwich, your longitude would not be the Greenwich hour angle. The Greenwich hour angle would be measured west from Greenwich all the way around. So it would be like really, really big, 350 degrees, for example. So that's the main difference between GHA and declination, is that it is measured just westward from the Greenwich meridian. A meridian is a line of longitude. Let's take a look at a quick example problem for this GHA business. And so for example, if we were looking at the 18th of April, 1981, and we wanted to know the GHA of the sun at exactly 1700 GMT, what would we do? Well, we're going to go into the daily pages of the Nautical Almanac and we'll look for the 18th of April. So remember that there's 3 days typically on each page. So we're looking at the lowest date in this case. And the sun is going to be on the left side of the right-hand page of the Nautical Almanac. So there's GHA and declination. We've looked at how to do declination before. Here's GHA. Let's pay a little bit closer attention to the numbers here on the GHA column and see what it explains to us. First of all, when we are at 1200 GMT, the GHA of the sun is very close to 0. So noontime is typically when the sun is highest in the sky or it's at the same longitude as you. And so in the Nautical Almanac, everything is in GMT. So when the sun is directly over, the longitude of Greenwich or the prime meridian at noon, the GHA is practically 0 because the sun is right there. It also moves at a rate of about 15 degrees per hour, you can see, right? And then it starts to get greater than 180 after midnight. And then it continues increasing about 15 degrees every hour until it hits noon again and a new day starts. So just think about how that works as the Earth rotates underneath the sun. For our purposes, we're looking at the 18th of April at 1700 GMT. What is the GHA? Well, we simply pull it off the table as 75 degrees, 10.8 minutes, and that would be our solution. So we'll learn more about this in detail later, but this is a good start for GHA in the Nautical Almanac. One key skill that we're going to need to use when we do celestial navigation, if we're going to use the tables, is called interpolation. Interpolation just means choosing a value that may be not listed on a table that you're given. So for instance, in this case, if there's a certain category and a certain time, we can see that at 11 o'clock, category 1 registers 26, and at 12 o'clock, category 1 registers 28. So if I asked you to determine the value here at, say, 11:30, well, you can use your brain and mentally interpolate and say, okay, well, if at 11 it was 26 and at 12 it's 28, it's clearly going to be 27 at 11:30. That skill is very important, and typically, to be honest, you can mostly mentally interpolate declination as an example. GHA and other categories are a little bit harder to mentally interpolate. So instead, what you need to do is use ratios. So let's imagine instead of 11:30, we were interested in, say, 11:40 for category 2. You can probably mentally interpolate that as well, but if not, let's just say, okay, the process is going to be, all right, the value difference here is 3, and the value difference here is 1 hour or 60 minutes. You could choose kind of what your number is going to be. In essence, on the left side here, we are 2/3 of the way from 11 to 12. We've gone 40 out of 60 minutes, or we've gone 0.6 out of 1, or 0.666 out of 1 hour kind of thing. And over here, we've gone how many out of 3? So if we were to set up a ratio, you could say, okay, on the left side, we've gone, let's say, 40 out of 60 minutes. And on the right side, we've gone an unknown number out of 3. So if you were to reduce this fraction, first of all, it's very easy to do that. You could just get rid of the zeros. Or you could make this 2 out of 3. you can see that x is going to equal 2 in this case. So what we need to do is if we added, 2/3 of an hour over here, we need to add 2 units to this and get 77. So at 1140, the value would be 77. The good news is you don't have to do these ratios all the time when you're using the Nautical Almanac. Instead, there are going to be little tricks such as these little numbers down here, as well as information in the back of the book which help you do some of these interpolations using the tables. It is a good skill to have just in general though, to be familiar with how to kind of mentally interpolate or how these tables are created. So develop this skill over time. It's not critical for solving celestial sight reductions right away, but as you become a better navigator, you'll find that interpolation is going to be an important skill that you want. All of the times noted in the Nautical Almanac are given as Greenwich Mean Time, otherwise known as Universal Coordinated Time. It's a good skill for a mariner to have to be able to convert between time zones. While we're in the Nautical Almanac, I did also want to mention that time zones are given for almost every place on Earth in terms of land locations towards the back of the Nautical Almanac. But let's talk about time zones in more detail. Since there are 360 degrees in the spherical Earth and there are 24 hours in an Earth day, each time zone is going to be 15 degrees wide. The 0 point for the Earth's longitude is Greenwich Mean Time. Greenwich, England is here. This is also known as the prime meridian. Right? And that's kind of the 0 point for the time zone, which correlates to GMT. It's going to be 7.5 degrees on each side of that. So from 0 to 7.5 west or 0 to 7.5 east is kind of the GMT time zone. However, we don't usually note it that way in terms of celestial navigation. Instead, we think in terms of the whole value of a time zone west or east of Greenwich. So if this was 15 degrees, 30, 45, etc., or 15 degrees east, 30 degrees east that way, each time zone is going to be on its standard meridian. When we dive in a little bit deeper onto these standard meridians, let's kind of flatten the Earth out and say that this is GMT and this is 15, 30, 45 degrees west. Each of these time zones is going to have what's known as a zone descriptor. So this one might be +1, this one might be +2, this one might be +3. What this means is it tells you the amount of hours you need to add to your local time to get to Greenwich time. So for example, if our local time here was say 10 o'clock and we added 3 hours to it, we would get Greenwich Mean Time of 1300. If our time here was 11 o'clock and we added 2 hours to it, we would get our Greenwich Mean Time that way. It also works in reverse. If it was, say, 1800 GMT, and you wanted to know what the local time would be, simply subtract 3 hours to get it. So 1500 would be the local time in that case. If you go the opposite direction, so if we were in the Eastern Hemisphere, and this was GMT here, we would have 15, 30, 45, etc. east. And these time zones would correspond to -1, -2, and -3. So same rules would apply. If the time here was say 10 o'clock, local mean time, we would subtract 3 hours to get the GMT of 0700. Likewise, if it was 0900 here on -2 time zone, we would subtract 2 hours to get 7. Vice versa works as well, just like in the Western Hemisphere. These time zones are corresponding to these longitudes. So you'll often see in the math problems, you are observing time zone descriptor -3, your longitude is roughly 45, and you might need to convert some times in that case. Time is very important as we move forward into celestial navigation. Just remember the key fact for now is that things are going to be in GMT in the Nautical Almanac. So you need to have the ability to take your local observation, shift it to GMT so that you can get the correct data out of the Nautical Almanac. One principle of living on a rotating sphere is that clock time and the degrees and minutes of arc are related. For example, we've already learned that the Earth rotates 360 degrees in 24 hours, or 15 degrees per hour. Importantly, this is in relation to the Sun. The Nautical Almanac has two tools that are very helpful when it comes to converting arc and time, vice versa. The first is the conversion of arc to time table located near the back of the Nautical Almanac. As you can see, there are degree graduations here, as well as minutes and fractions of minutes on the right side of the screen. There's also instructions at the bottom which indicate that the table is for converting expressions into their equivalent time if they are an arc. Diving in a little bit deeper, we can see that, along the left-hand side here, for example, 1 degree of arc is equal to 4 minutes of time. And this is for the Sun, and longitude is what we're talking about here. Likewise, around 15 degrees of arc is equivalent to 1 hour of time. So this is something we've talked about before, but here it is laid out in a table. If you ever needed to convert arc to time in a minute or a fraction of a minute, you could generally choose the whole degree value on the left part of the table, and then you could use the minutes over here on the right side of the table, 0, 1, 2, 3 minutes, etc., and the fractions of a minute to add up an additional correction. These are summed together when you're converting arc to time. The next tool that's available to you is what's known as the Increments and Corrections pages. These tables are used for converting values of time, in terms of minutes and seconds, into angular values of arc for a variety of objects. So for example, let's dive in a little bit deeper on this page, and you'll note that this is the page for 2 minutes or 3 minutes. And so there's a whole bunch of these for each individual minute. Diving into the 2-minute category, there's 2 minutes and 0 seconds, and 2 minutes 1 second, 2 minutes 2 seconds. You can figure out the value of degrees and minutes of arc for this 2 minutes and 2 seconds of time, for instance. It'll be listed right there for the Sun. For Aries, which is used for stars, it's very similar, but just a little bit different than the Sun. Likewise, the Moon has its own category as well. So for example, if we were looking for the equivalent of, say, 7 minutes and 59 seconds of time, we would flip to the page where it says 7 minutes. So 7 minutes up here. And we would scroll down until we got to 59 seconds. So as we dive in even a little bit deeper, we see that 7 minutes and 59 seconds is equivalent to 1 degree, 59.8 minutes of arc for the Sun. All right, so these values are listed for you there, and you can pull them out for any minute or any second of time and convert them to arc, or use the conversion of arc to time tables to convert things back the other way. Adding and subtracting time or arc measurements can be tricky, but it's a routine task in celestial navigation. Here's a few tips. When you're adding or subtracting time, separate the hours and the minutes, and then you can always borrow 1 hour to make more minutes if it's easier for you to do this math over here that way. Likewise for arc, remember that there are 60 minutes in 1 degree, just like there are 60 minutes of time in 1 hour. So it's not like 100 that you can borrow. When you're adding and subtracting degrees and minutes of arc, it's likewise helpful to kind of break them apart into their degrees and their minutes, and then borrow as necessary from there. So let's take a look at two quick ones. If it was 0 to 14 and we had to subtract 11 hours and 51 minutes, that might be kind of a tricky problem. So the way that I would approach it, I would change this into 0, 1 hours, and I would change this into 74 minutes. So I borrowed an hour and I added 60 minutes in that case. And now I can do the math a little bit easier. 74 minus 51 is 23. And then since it's a new day, we can change this into 25 hours. Since we're just adding a day or subtracting a day, you're allowed to do that. So 25 minus 11 would be 1423, the previous day. You're going to encounter this kind of stuff a lot when you're converting to or from Greenwich Mean Time. For arc, we often have to subtract things, whether it's for determining hour angles or just for traditional HS to HO type stuff. This is a little bit of a big one, but in this case, the same deal would apply. I'm going to borrow 1 degree and make this 46. And then I'm going to make this 72 minutes. So I put 60 minutes over here and I borrowed 1 degree. So 72.2 minus 56.8. I can do that pretty quickly or use a calculator if necessary, and it's 15.4 minutes. And then 46 minus 22 is 24 degrees. So adding time is generally a lot easier. You can just make sure that you convert anything over 60 minutes in either side to degrees or to hours, as the case may be. This is something that takes practice, but it is a critical skill for some of the stuff we're going to do in the future. You may remember from middle school math class that speed and acceleration are related. For example, speed might be something that we would note in terms of meters per second. Acceleration measures the rate of change of speed. So acceleration might be meters per second or meters per second squared. These two are different, but they're related. In the Nautical Almanac, there are a host of these little corrections which are known as V and D corrections. At this point in the course, it's helpful to learn about them in general, and we'll learn how to apply them specifically later. First up is the D correction. So for example, the sun has a declination and it changes from hour to hour. The hourly change in declination is located down here, the D of 0.7. So you'll use that each day when we're trying to determine the declination. Likewise, the declination of Venus, Mars, Jupiter, Saturn, they all have D numbers as well, and the moon does too. V numbers are really related to that rate of change that we talked about, kind of the acceleration or the deceleration of the GHA of objects. And so down at the bottom of each page, there is a V correction for these. So I'll show you these in a little bit more detail. So for example, on the fourth here, there's Aries, there's Venus, Mars, Jupiter, Saturn, and they all have V corrections. These are rates of change correction that we'll learn to apply in just a minute. Of note, stars also have a declination, but there's no D number because stars' declination does not change very quickly at all. The moon is a very challenging thing to deal with, so it's got a V correction for every hour and a D correction for every hour. So what do you do with these corrections? Well, we'll learn about them specifically for each object as we go forward in the course. But in general, what you'll do is you'll use the increments and corrections pages. So for whatever time that you're interested in correcting for, there's a table which has V or D correction in there. And so for instance, if you had 44 minutes of time for whatever case you're working on, and you had a V correction of 7.5, well, your answer is going to be 5.6. Really what this is saying, if you look closely, like if we look at, say, 0 minutes, we'll note that if your V correction is 8.0 at 0 minutes, up here, well, your correction is actually 0.1. It's very, very small. As the hour goes on, the correction gets bigger and bigger because you're moving through the hour, such at the point where it's at the end of the hour, your 8.0 V or D number at the end of the hour at minute 56 is going to be very close to that 8. So that 8 represents an entire hour of change, and the V or D correction kind of deals with it that way. So V and D corrections are put in for different bodies, and they're treated slightly different in each case. But the way that you apply them is pull the number from the daily pages, use the minutes page of the increments and corrections, and use this as a table of corrections. All right, so far we've done a lot of good stuff. We've learned how to, for instance, determine the declination in GHA of a sun at any particular specific hour. We've also learned to use the increments and corrections pages in the Nautical Almanac. And we've learned a little bit about V and D numbers, as well as time, and adding and subtracting time and arc. So it's time to put it all together. This is a core skill. It's very, very important. This is the crux of stage 2 of the celestial navigation process. What is the geographic position of the sun on the 4th of February at this very particular time? First of all, what is GP again? Well, it's the declination and the GHA of the sun. We want its latitude and its longitude west of Greenwich so that we can move on into step 3, 4, and 5 by building and solving triangles. The steps to this are basically going to be to use the Nautical Almanac's daily pages for 04 February, get values for 0800, then use the increments and corrections pages to account for this 2212, and the D or V corrections to just make little tweaks to these along the way. So here would be my process. So I would open the book to the 4th of February. And I would look, so here's the 4th in the middle here, so we'll zoom in a little bit. I would look for the declination in GHA at 0800. So here's 0800 Greenwich Mean Time. So the declination is south 16, 12.7. So we'll note that over here. South 16 degrees, 12.7 minutes. I would also note the direction of change while I'm in here. So 12.7, 11.9, 11.2, so it's decreasing. So I'm going to note that it's decreasing. And I'm going to note the D number down here at the bottom, 0.7. So I'll write that down as well. 0.7 equals little d. So we're good with declination for now until we get to the increments and corrections pages. But while we're here, let's also record the GHA of Greenwich at 0800, 296, 30.5. So that's 296, 30.5. So that's the GHA and declination for 0800 hours, the whole number of hours. But we still have to account for the 2212. So we'll do that in the increments and corrections pages back here. So we'll flip to the page for 22 minutes, which is right here. And then if we roll down here, we've got 22 minutes and 12 seconds. And in the sun and planets column, there's going to be a correction that we can apply to the GHA. So 22 minutes, 12 seconds, looks like we need to add 5 degrees and 33 minutes to the GHA. So we'll note that over here, 5 degrees, 33.0, and it's always added because things are always moving west of Greenwich. So let's solve this right now. And we've talked a little bit about adding degrees and everything. So 30.5 plus 33, I would write this as 63.5, and then I would solve this part and say 301. But you can't have 63 degrees, so I would take away 60 and make it 03.5 and add a degree over here. So the GHA of the body is 302.03.5 for this very specific time. What about the declination? Well, we noted that the D number was 0.7. So on this very same page, we're going to look in V or D correction for 0.7 right there. And then the correction is 0.3 that we would pull out of it. So that's what we need to either add or subtract to the declination. So it's going to be 0.3. How do we know whether to add or subtract? Well, we noted earlier that the trend was decreasing, so that means we're going to subtract. So it's going to be south 16 degrees, 12.4. So this may seem straightforward, it may seem not straightforward, but this is a core skill. So I would encourage you to spend a significant amount of time practicing this, because once you have this, you've got step 2 of the process locked in. Once you have learned to find the geographic position of the sun at any time, that's like the base calculation, and it's a really good start, and you probably have a pretty good understanding of all this going on. But if you wanted to find the declination GHA of the various planets at any time, well, that's a little bit of a different story. So declination for planets is always listed next to the planet. So for Mars, for instance, or Jupiter, or Venus, or Saturn, it's going to be listed right next to the planet in question. Likewise, the GHA is listed in the planet column, and there is a V correction definitely for the planets. Sometimes it's a negative correction, in which case you would need to apply the sign that way. So taking a look real quick at the Nautical Almanac for planets, You can see what I'm mentioning here, that the planet is located here. Up here is just the intensity of the light of it. And then there's the GHA and the declination of each individual planet. Down at the bottom, there are V and D corrections. You would use them the same way that you do the D correction for the sun, but the V correction is just an additional correction that you need to make. All right, zooming out on the solar system a little bit into interstellar space now. If we've got our nice night out there, we've got the stars out there, and stars are a little bit unique because instead of listing the GHA for each individual star, the Nautical Almanac would be huge in that case. They list the GHA for the first point of Aries. The first point of Aries, incidentally, is just a designated spot in the sky, similar to kind of like GMT. It's the point in the sky that's directly over Greenwich on the vernal equinox. It's kind of like the Greenwich of the sky. But anyway, the Nautical Almanac just lists the GHA of Aries, and then it asks you to make a correction called SHA for each individual star of the navigational stars. SHA is sidereal hour angle. It's just an additional hour angle that we need to account for. And if you were taking a look at kind of the Earth in general and these hour angles, which we've spoken about a little bit, this might be, GMT here, and right up in the sky is the first point of Aries. Well, as Aries moves around the Earth, or the Earth rotates underneath it, it's going to have a GHA as it rotates around. The stars would then have, an additional correction for any additional star. So this is SHA, this is GHA, and the totality of it is the GHA of the star. You don't need this theory to kind of understand it. Really, in the Nautical Almanac, it lays it out for you. Over here is the GHA of Aries. Note that there's no declination because nobody cares about Aries particularly. But each star then has an SHA, a sidereal hour angle that would be added to Greenwich hour angle to obtain the GHA for the star. Additionally, the stars have the declination listed right next to it. The declination does not change that much for stars over the course of a year. So you can just use it for any point in a given day, or a couple days actually. Right? So the process for finding the Greenwich hour angle of a star is first find it for Aries and then add the SHA to get it. If you end up over 360, you can subtract 360 to make it a real number. Finally, zooming back into our own Earth and Moon system. We've got the Earth and it rotates around, and we've got the Moon and it's pretty darn close to us. So as we've talked about earlier, there is a little bit of horizontal parallax. The lines of light from the Moon are not exactly parallel like they would be from a star, which is like way in the distance, or even the sun. Also, the Moon's orbit, no orbit is perfect, so it kind of oscillates a little bit. And over the course of the Earth, you're going to end up having different kind of orbital planes for the Moon, which will result in different positions. And those positions are going to change very quickly for the Moon. So declination for the Moon changes extremely rapidly and requires a D correction every time. So over here in the Moon column, there is declination. You can see how quickly it changes, and a little D correction for each hour. Likewise, the GHA of the Moon changes and the rate of change changes as well. So the V correction is going to be a way to account for that. The horizontal parallax is the place to look over here, and we learned in step 1 of the process what to do with that, but that's where it's going to be. You note that the horizontal parallax doesn't change that quickly, so you can generally use it for an entire hour. So finding the geographic position of the Moon, the planets, and the stars is relatively straightforward once you've known the process for the sun, but if you follow these notes and do some practice, you're going to be in good shape going forward. Although not strictly part of the celestial navigation process, that's our kind of main quest here, determining the time of sunrise and sunset is a key skill that's helpful to introduce at this point in the course. The sun is generally observed during the day when it's about mid-morning or mid-afternoon for reasons that we'll describe a little bit later. But most celestial objects of stars and planets and the moon and whatnot happen at twilight. when the horizon is still visible, but so are the celestial objects up in the sky. So there's several ways to determine the time of phenomena, as we would phrase this. In this course, we're going to focus on what I think is the shortest and easiest way. The basic principle is, if you're on the Earth, the Nautical Almanac is going to list times of sunrise, sunset, twilight, etc. for all standard meridians, so 15, 30, 45, etc. They're also going to give them for tabulated latitudes, say 40 degrees and 50 degrees. If you're somewhere in the middle, just like many processes in celestial navigation, you just need to take the tabulated values and apply an offset to get your exact time. The general process is going to be to open to the daily page of the Nautical Almanac and look at the times of twilight, sunrise, moonrise, sunset, evening twilight, and moonset. The times of moonrise and moonset are seldom needed to be very exact, so we won't really focus on that too much. If the moon's in the sky, you kind of know it. But sunrise and twilight are very effective, and so is sunset. So you'll notice that, say for sunset here, there's no longitude given. That's because these are for every standard longitude, every standard meridian. So at latitude 40 and longitude 15, the sunset will be 1925 local. At latitude 40, longitude 30, local time, it'll be 1925 as well. So one important thing to note is that whenever you're going to be interpolating times of sunrise and sunset from the table, it is important to note the times that are below what you're interested in. So if you were interested in 41, you are going to use 40 and 45 as your bracketing latitudes, but you're going to make all corrections based on the time at 40. That's because the Earth is a sphere, and this is not a linear interpolation. It's a curved interpolation. The other tool that we're going to need for this process is going to be the Table 1, which is near the back of the Nautical Almanac, tables for interpolating sunrise, moonrise, etc. So Table 1 for latitude, and we'll really just need this for our purposes for the sun and twilight. Note what the table is asking you, and there's also instructions here. But the tabular interval refers to whether there's 10 degrees, 5 degrees, or 2 degrees between the daily pages. So, for instance, you can see the latitude differences change with latitude. Likewise, the difference between the times for consecutive latitudes is referring to the difference between, say, the time for latitude 58, which is 0448, or the time for latitude 60, which is 0445. So that would be 3 minutes. You can always round to the nearest value in here. And then finally, the correction in here, like I said, is going to be applied to the time just below the time that you're looking for. The easiest way to focus on this is, let's imagine we're working an example problem. It's August 4th, and our ship's position is 25 degrees north and 65 degrees west. We're interested in the time of sunrise. So you don't have to look in the daily page per se. As long as you're on the right page itself, you can look at the sunrise times. So first of all, we'll note that at latitude 20, the time of sunrise is 0536. At latitude 30, the next highest, the time of sunrise is 0520. So it's decreasing with latitude. The time is getting earlier with latitude. Remember, these are all standard meridians. So we're going to make a latitude correction and then a longitude correction, and we're going to be good. So we need to note that the tabular interval is 10, and the value we're looking for is right between them. We also need to note that there's 16 minutes of difference between these. So if we flip over to Table 1, we're going to be in the tabular interval of 10 column, and our value is 25 degrees north, so it's exactly halfway between, but it's 5 degrees above the lowest tabulated value. And then we're looking for the difference between the times for consecutive. So that was 16 minutes. 16 minutes is not noted. We can just estimate to 15, and we'll note that our correction in this case is going to be right in this vicinity here, right? So 7 minutes. You could interpolate that to maybe 8 minutes. So as long as you're working with an accuracy of somewhere between 3 and 5 minutes, you're going to be perfectly fine. So 7 minutes or 8 minutes is going to be an appropriate solution. So in essence, what we did with this process so far is we created some bracketing values. We set at latitude 20 north, the time was 0536, and at 30 north, the time was 0520. So it's clearly getting smaller. Our latitude was it was 25 degrees north rather. And these are all standard meridians. So 60, 75, etc. So the first thing to do is take the lowest latitude value, 0536, and apply that correction, which was 7 or 8 minutes. Let's call it 8 minutes. And we'll get to 0528 for our latitude corrected time. The next step is to just make the little correction to get us to 65 instead of 60. So we're west of the standard meridian, which means we're going to be later. If we were east of the standard meridian, it would be earlier. So we just need to convert 5 degrees of arc into time. To do that, we'll use the conversion of arc to time tables in the Nautical Almanac, which are located towards the back. We'll notice that 5 minutes of arc is equal to 20 minutes of time. And so we can kind of apply that either earlier or later. In our case, we said it was going to be later. So we'll take 0528, the latitude corrected time, and we'll add 20 minutes to make it later, 0548, which would be our final answer. Again, if our standard meridian was, say, 60 in this case, we were west of it, so we need to add time because the sun moves from east to west. If we were east of it, if our latitude was 55, or our longitude was 55, let's say, we would be subtracting in that case. So always pay attention to the standard meridian and which side of it you're on for the longitude correction. So kind of in summary for this, it's going to be number 1, correct for latitude. And to do that, we'll use table 1 in the Nautical Almanac. Step 2, convert arc to time to correct for longitude. And then you can get any phenomenon, sunrise, sunset, you can get twilight. And then for the moon, there's a tiny different process. But again, times for moonrise and moonset are seldom needed, even according to the Nautical Almanac. So practice this skill, and it's going to be a good quiver in your arsenal of weapons for celestial navigation. The noon site for latitude is a very historic and useful site. So this is probably one of the first skills at this point in the course that you can do completely. You can get a latitude from the sun at noon and navigate your way across an ocean that way. So first things first, there are 2 terms that we need to brush up on. One is declination. I think we feel okay about that. Typically, we've drawn declination as, the latitude of the GP. So the geographic position's latitude is the declination. There's a different way to represent declination. So if we were to take the Earth and then chop it in half with a lightsaber, this is the center of the Earth. This is the equator. The equator goes out into space and to become the celestial equator. And declination could then be represented as this kind of angle here. So you're looking at the Earth cut in half. This is the center of the Earth, so it's an angle. Declination could be in the south as well. It really depends. It varies based on the object that you're looking at. It varies with the seasons and everything. So think about a way to represent declination that way. Another term that we need to talk about is what's known as zenith distance. So going back to our original diagrams of the Earth, we're looking at it from space, and maybe this is like the GP of the star or something. You've got its declination, you've got its GHA, and then there's some spot where we are as well. So that's our dead reckoning position, or where we actually are. If you were to take this distance right here, the distance from the GP to you in your boat, that's a real distance in nautical miles, and it's called zenith distance. You can actually get that by taking your sextant reading and saying 90 degrees minus your sextant equals zenith distance. So it's just the inverse of the sextant reading from 90 in essence. So 90 degrees straight above your head is the zenith, and the sextant reading, wherever that is, kind of the leftover part is the zenith distance. So let's draw it from a different perspective here. Just like we drew declination with the center of the Earth cut in half, we'll draw zenith distance the same way. So here's the center of the Earth, there's the equator, and let's say you are floating on your boat up there. You could represent your latitude with this right there. That would be your latitude, right? Well, the spot directly above your head is known as the zenith. The zenith is right over your head. The nadir is directly beneath you. So when you're feeling, not the best, you're having a nadir of a day kind of thing, right? Zenith distance is if you were to take say the GP of the sun or something and drop it down to the Earth, it's going to continue all the way to the center of the Earth as well. And so this would be the declination of the celestial GP. So where it hits the Earth, the latitude of that is the declination. So this right here is zenith distance. So it's the distance from you, your latitude, to the celestial body's latitude in this kind of diagram that we're looking at here. Remember, there are a couple ways to portray this. Another way to think about zenith distance is if we were to zoom in on ourselves just a little bit. So if we had, say, your eyeballs right here, this would be your zenith, and this would be the horizon. The sun is somewhere up there in space, and you use a sextant to measure this angle from the sun to the horizon. Zenith distance is the complement of that angle. So it's this right here, the distance from the zenith directly overhead to the star. And mathematically, that's actually what we're most interested in. So when we take our sextant, we're looking at the sextant, through the sextant to the body, down to the horizon. What we're truly interested in is from the body to our zenith. That way, mathematically, we can do all the things that we want to do with our celestial sight reduction process. So declination, zenith distance, let's just kind of review those terms. So getting back to the noon sight for latitude in the historical sense, let's just imagine there's an old continent here. So continent number 1 is there, and there's like a new continent or a new island over here. So this is continent 2. This area is familiar to people. This area is new, it's unexplored, but we know the latitude of it. So the latitude is, say, 12 degrees north. When you leave the old world, the familiar world, you might be leaving from this harbor here, and you're going to navigate down the coast using piloting techniques. You're going to look at landmarks that are familiar, you're going to look at charts, and then eventually you're going to head off into the ocean. There's no land around, there's only the sun. So what you can do, and what the early explorers did, is they would every day at noon, when the sun reached its highest point in the sky for the day, they would take a measurement, which is what we're going to do in this lesson, and they would determine their latitude. And they would say, okay, hey, my latitude is 15 degrees north. Well, I need to turn south. The next day they would do it. All right, it's 14 degrees north. I need to keep going south, and so on and so forth. Eventually they would hit 12 degrees north, and they know, hey, I'm at the latitude of my destination, so if I just turn west, I can continue doing this and checking every day to make sure that I'm good, and eventually I'm going to run into land. I'm going to see birds and currents and sticks in the water and things, and I'll know that I'm approaching my destination. I might not be able to determine my longitude, but if I know I'm at the latitude of my destination and I continue west, keeping a careful eye out for wayfinding techniques, eventually I'll find my destination. So given that quick discussion of the terminology that we're going to use and the historical context, let's bring it all together and talk about the noon sight for latitude as it's observed today. So every day, if you were to sit in one position on the ocean, you would see the sun rise, transit, and then set in the west. If you were in the southern hemisphere, it would appear to rise from the east, transit, and set in the west. It just depends kind of what your perspective is. But rising in the east, setting in the west, and then eventually reaching its highest point in the sky for the day. When it does that, it's on the same longitude line or meridian as you. So if your longitude is 64 degrees 31.7 west, so is the sun's at the point when it's in the highest point in the day for the sun's altitude above the horizon. When its longitude is your longitude, all of the celestial navigation math that we're working on in this 5-step process collapses down to a special case. and you can plot a latitude line given just a little bit of data, declination, zenith distance, and you're pretty much good to go. So let's demonstrate kind of some of the cases of how this can work. Thinking back to our diagram of the Earth cut in half with the lightsaber, this is the center of the Earth, this is the equator that goes out into space, and let's stay in the northern hemisphere for this discussion. Well, we want to get our latitude. So this would be our latitude, our distance north of the equator. This is our zenith above our head, and somewhere out there there is a star or a sun or a moon or a planet, and if you dropped a weight down, it would impact the Earth and then continue down to the center of the Earth. This right here is declination. Declination, which we can look up in the Nautical almanac. You're pretty good at that at this point. This right here is zenith distance. And zenith distance equals 90 minus your height observed, or the sextant height. Your sextant measurement. Once you've corrected it, it's height observed. So really, if we can determine the declination of an object and look it up in the Nautical almanac, if we can take our height observed from 90, we have zenith distance, we have declination. In this case right here, latitude equals zenith distance plus declination. So we just need to create a formula and we can calculate our latitude. So this formula works when you and the sun, or whatever body, are in the same hemisphere and the sun is further to the south than you. Let's think of a different circumstance. What if the sun or the other body was in the other hemisphere? We drop it down like that. The equator goes out into space. This is declination. This is zenith distance. So all the way to the sun. And then latitude is that. So in this case, latitude is going to equal zenith distance minus declination. So that's another formula that we've got. So if you and the sun, or you and the celestial body, are in opposite hemispheres, latitude equals zenith distance minus declination. There's more cases though, so we'll take a look at kind of all of the cases. So what if you were in the northern hemisphere, let's say, but the sun was further into the same hemisphere as you? So you're closer to the equator than the sun. So the equator goes out here. This is your latitude. This is your declination. And this is your zenith distance. So in this case, latitude, which is, or this one right here, latitude, would equal declination minus zenith distance. So if you're in the same hemisphere as the sun or the other celestial body, but it's poleward of you, if it's closer to the pole, or if you're closer to the equator is another way to do it, zenith distance latitude is going to equal the declination minus the zenith distance. There's kind of two other cases as well, which you might not be thinking of right now, but they do exist. You and the body are on the exact same latitude line. So if the declination in this case is going to equal your latitude. So this would happen when the sun is directly overhead, when the sextant reading is 90, which is pretty hard to actually pull off in real life, but latitude could equal declination in that case. And so sometimes, like in Hawaii or in the tropical islands around the world, everywhere between the Tropic of Cancer and the Tropic of Capricorn, at some point during the year, latitude and declination are equal. The sun is directly overhead. So that's kind of a unique case as well. And then our final case, which only happens very rarely as well, is when the sun or the celestial object is on the equator. So in this case, right, your latitude is going to equal your zenith distance. So these two are rare, but unique. So if you're a celestial navigator or a math nerd and you're ever interested in this stuff, those are kind of cool. But these are our three main cases. Latitude could equal zenith distance plus declination if you're in the same hemisphere and the sun or the celestial object is closer to the equator. If you're in the same hemisphere but the sun is closer to the pole, latitude equals declination minus zenith distance. And if you're in opposite hemispheres, latitude equals zenith distance minus declination. Let's take a look at some example problems about how to solve these, because it's very cool and it's a nice thing that you can actually accomplish with the skills that you've got right now. In this first example problem, our dead reckoning position is 44 degrees north, so that's roughly where we are. You're never going to be dropped into the middle of the ocean, so that's why we list the DR position. You'll always kind of roughly know where you are. Our declination, 15 degrees 15 minutes south, so that's the sun's, the GP latitude is the declination. And our height observed, 30 degrees 30 north, so that's the sextant height corrected for index error, dip, refraction, etc. So first thing I would do is let's represent our situation here. So this is the equator, and the declination of the sun is down here somewhere. So that's our declination. We are up here somewhere in the northern hemisphere. So this would be our latitude. The last thing to consider is the distance from the zenith to the sun is zenith distance. So this is going to be a formula where latitude right here is going to equal zenith distance minus declination. So if we just find these pieces of data, we've got our latitude. Well, declination is 15 degrees, 15 minutes south, so that's great. We just need zenith distance. So remember, zenith distance is equal to 90 minus the sextant height, or 90 minus the HO. If you do it with hand math rather than a calculator or a program, I like to write 90 degrees as 89 degrees and 60 minutes. It helps me with my arithmetic. So then the height observed was 30 degrees and 30 minutes. So that's some quick math right there. So we can say that our final zenith distance is going to be 59 degrees and 30 minutes, right? So 59 degrees, 30 minutes goes here, minus 15 degrees, 15 minutes, is going to equal our final latitude of 44 degrees and 15 minutes north. So that's a latitude you can plot on a chart. We've got it in with just declination and our sextant height observed. We were able to get a latitude and really plot that onto the chart. So that's fantastic progress given what we know from our previous studies. So in our second example, we've got a little bit of a different situation. So we've got our dead reckoning latitude. Again, you'll never really be thrown into the middle of the ocean without knowing roughly where you are. Your height observed is 7315. That's your sextant height corrected for dip, index error, refraction. And our declination, which was looked up in the Nautical almanac, was 20 degrees 20 minutes north. So in our situation here, this would represent declination, and this would represent latitude, and then this would represent zenith distance, the distance from your zenith to the celestial body up in the sky. So our new formula is going to be latitude equals zenith distance plus declination. So we just need to find these pieces of information. We can get our latitude. So declination was 20 degrees 20 north. We looked that up in the Nautical almanac. And then zenith distance is 90 degrees or 8960 minus 73 degrees 15. So if we kind of do that math out, we've got 16 degrees and 45 minutes for our zenith distance. So now we just need to add these two together to get our latitude. So the final latitude ends up being 37 degrees 05 minutes north. So again, with just our height observed, which we learned in step 1 of our course process here, in our declination, which we spent a lot of time in step 2 discovering, we can kind of get this latitude. The key is to make sure that the observation happens at the time when the sun is highest in its sky for the day, because otherwise this HO is going to be messed up and we won't end up with an accurate latitude. In this final example, we'll illustrate the third case. You know, we understood that there's kind of 3 cases we can majorly find ourselves in with these LAN problems. So in this case, we are in the southern hemisphere because our DR latitude is 11 south, but we're closer to the equator than the sun, in this case, whose declination is 15 degrees 40 south. So we looked that up in the Nautical almanac to achieve the declination using all the things we've learned here in step 2 of our process during this part of the course. Our height observed was our sextant height corrected for index error, dip, refraction, etc. All the stuff we learned in step 1 of this course. So now we just need to think of a formula. So in this case, latitude, which is this, is going to be equal to some relation between zenith distance and declination. Let's see if you can work it out for yourself. This would be zenith distance and this would be declination. So latitude will equal declination minus zenith distance, kind of the third case that we can find ourselves in most of the time. So declination, we can look that up. It's 15 degrees 40 minutes south. And our zenith distance we need to calculate. So I like to do 89 degrees in 60 minutes. You can do whatever technique works for you. Minus 85 degrees 12 minutes. And that'll get us our zenith distance of 4 degrees and 48 minutes. So if we subtract here, minus 4 degrees and 48 minutes, we'll end up with our latitude. Well, this is not something you can put into a calculator typically, so we'll use some more arithmetic tricks here. And so I'm going to borrow 1 degree, make this 14 degrees, and that becomes 60 extra minutes. So that's 100 minutes of arc there. So 100 minus 48 is 52 minutes, and 14 minus 4 is 10 degrees. So we've got 10 degrees, 52 minutes south, which is close to our DR latitude, which is perfect. So the noon sight for latitude is an awesome skill. It's very rewarding. It's usually pretty quick to do out there on the real ocean with a real sextant. And just to kind of make it hit home, in step 1 of our process, we practice with the sextant, determining the sextant height, correcting it for index error, dip, refraction, and sometimes some abnormal cases as well. So we really went from HS to HO, and we can determine that very precisely. In the second part of this course, we focused on the GP of the sun, finding the GHA and the declination of the sun. And it turns out for the noon sight for latitude, you just need the declination, and we can do some cool stuff with that, which is great. So with step 1 and step 2 of our 5-step celestial process done, you can already calculate your latitude anywhere on Earth. And people have used just this to cross oceans before. So if you go no further in your studies than celestial navigation than the noon sight for latitude, you're going to be doing perfectly fine. If you do want to continue your studies, well, here's what's coming next. This is a special case. And in essence, what's happening is that the sun is crossing your meridian. So the sun is somewhere on your meridian. And all of this, the North Pole, you, the sun, and the South Pole all form a line. That's kind of a special case of what typically happens during celestial navigation sight reductions. In other cases, if the sun is over here or if the sun is over here, we're going to start building triangles instead, using the North Pole, our position, and the sun's GP, or any celestial body's GP. So in step 3 of our process, we're going to build triangles using some thought and some deliberate action. In step 4, we'll use some tools to solve those triangles. And in step 5, we'll calculate a solution to that triangle and compare it to what we learned in step 1, the height observed, to be able to plot this on a real chart that's helpful to us. So that's a preview of what's coming next. But like I say, if this is as far as you go, this is exceptional work, and you can do some amazing things out there on the ocean. So we'll see you forward into step 3. Happy navigating.